Okay, welcome to lecture here. Um, we'll get going here in just a sec. Continuing on chapter 5. Sorry about that, a little technical difficulties. Let's go. Okay, so we've been talking about chapter 5. We talked about last time in lecture with everybody the idea of grams, moles, molar mass, Avogadro's number, uh, converting from grams to moles, moles to grams. And again, that conversion between grams to moles is a super common conversion that you need to use a lot in chemistry. Again, using Avogadro's number, which is really our conversion to go from moles to molecules or atoms back to moles. Um, and then sort of individually, each of you guys in terms of discussion the last couple of times, we took care of the balancing of equations and how to balance equations and different types of reactions, which again is not technically, I think, in this chapter, but or really anywhere in the book, I think. But we did talk about those different sort of types of reactions. Um, so before we continue on, kind of putting both of those things together here with the rest of chapter 5, let's just kind of go over, that calculation part of it one more time, just to make sure everybody's on the same page. So let's just make up one here. Let's say we have let's say we have 32.5 grams of C2H4O2, and we want to know how many molecules that would be. So why don't you take a minute or two here and sort of come up with that. In case you don't have a periodic table near you, carbon is 12.01 grams per mole. Hydrogen is 1.008 grams per mole, and oxygen is 16 grams per mole. All right, so see what you come up with. Again, we talked about this last time. Just make sure everybody again's on the sort of the same page here, and then we'll go with it. And I will calculate it as well since I just made it up to see if we all get the same answer here. So if you're just coming in, again, we're going to do this example here that's on the screen. So give it a go, and then we're going to talk about it. Okay, so I see some answers coming through, so it's looking good, I think. So let's take a look and see. So first off, as we were talking about last time, again, you don't always want to use Avogadro's number. Again, you just want to make sure you use it if it asks for something about atoms, molecules, or something like that. So clearly in this case, we're looking for molecules. So we do need to use Avogadro's number, which basically is that 1 mole is 6.022 times 10 to the 23. And again, that can be atoms, that can be molecules like it is in this case. That also tells us that in order to use Avogadro's number, we kind of need to get things into moles. So what we're starting with is grams. So if you remember, sort of our conversion to go from grams to moles is our molar mass from the periodic table. So really that's sort of where we want to start with this calculation. So when we calculate the molar mass, we pretty much just go to the periodic table and we pretty much add up everybody that's there. So 4C2H4O2, we would have 2 times 12.01, which is again from the periodic table for carbon, plus our 4 times 1.008 grams per mole, which would be for our hydrogen, and plus 2 times 16 grams per mole, which would be for our oxygen. And if we add all of that up, that will give us the molar mass of this compound. And it looks like we get something like maybe 60.05 when we do that. And usually molar mass to about 4 significant figures is what you take it for. Like we talked about last time, essentially molar mass can be used as a conversion factor. But when we do state the molar mass, the number always stays with the grams part and is always per 1 mole. So that is the important part. Molar mass, always 1 for the mole, always the grams for 1 of basically the formula. So the first part of the calculation, we're going to do 32.5 grams of C2H4O2, doing a sort of dimensional analysis way, opposites in terms of units. So grams are on top here. So to get rid of the grams, we need to put the grams on the bottom and the moles up on top. And at this point, the grams will cancel. And if I stop right now, I'm at units of moles, and you could get an answer, or you could continue on with the calculation. So I'm going to continue on with the calculation here. So what I want to then use, now that I have it in moles, is I could use my Avogadro's number now. So same idea here. We want to go opposites in terms of units. So moles are on top. So the 1 mole will go on the bottom. Avogadro's number will go up on top. And these would be molecules in this case. We want to make sure that we, again, use our exponent button, but our moles will cancel, and that will leave us just molecules. So mathematically, what we're doing is we're taking 32.5. We're going to multiply it by Avogadro's number, 6.022, exponent button, so no multiplication button or anything like that, just the EE button, 23. I would hit equals. And hopefully your calculator doesn't die like mine just did. And we'll try that again. 32.5 times 6.022 exponent 23. We're then going to divide it by 60.05. And that is going to give us what I think I see in the box there. We are going to get 3.26 times 10 to the 23. And again, the units here will be molecules. Any question on those steps or molar mass, Avogadro's number, converting? Again, like I said, probably most of the time, you probably won't be using Avogadro's number too much, but a lot of calculations do involve that step where you go from grams to moles and using the molar mass. So it's very, very common. Any questions on that part of the calculation there? Okay, so as I mentioned before, we kind of talked about these calculations last time all together in lecture and previously in discussion for both discussion Monday and Wednesday. We took care of sort of balancing equations and all that. So where we're going to kind of pick up with the notes here is putting both of those things together. So we're going to put together the balancing of equations. We're going to put together grams and moles, and we're going to be able to use the equations basically to figure out certain things. Things like how much products we can make. We can also figure out how much reactants we started with. So we could do a lot of calculations from an actual chemical equation. And when we look at a balanced equation and we sort of look at those coefficients, we basically can kind of say several different sort of relationships that we see. One being, we could look at the coefficients, and since these are molecules, we could say for every 2 molecules of H2, it reacts with 1 molecule of O2 and gives us 2 molecules of H2O. And if you're wondering where the numbers are coming from, they are coming from the coefficients in the balanced equation. And that's what all this, what we're going to talk about, really is all about. This is what is referred to sometimes as the stoichiometry part of it. And it is nothing more than just the actual coefficient from the balanced equation. We could also say this relationship, that 2 moles of H2 react with 1 mole of O2, gives us 2 moles of H2O. This relationship here, which is really the mole to mole relationship from the equation, this equation pretty much is what we're going to use here to do these type of calculations, this sort of mole to mole relationship. Another relationship is, which is the conservation of mass, we don't lose anything along the way, is if we start with 36 grams of reactants, we should end with 36 grams of products. And that is because, as we talked about when we balance equations, if I started with 4 hydrogens on the left, I should have 4 hydrogens on the right. And since they both pretty much have the same mass, 4 on the left, 4 on the right gives me the same mass on both sides. So we're going to talk about stoichiometry, and stoichiometry really is nothing more than using a balanced equation as like a conversion factor. So that's essentially what we're going to do here. So stoichiometry is that sort of calculation, and sometimes people get really like scared about the whole stoichiometry part of it and all that. But essentially what it is it always starts, and something to keep in mind when you do these type of problems, everything has to start with a balanced equation, because we use those coefficients as the mole to mole relationship. So we need to make sure that it definitely is balanced, but it allows us to basically figure out a lot of things just based on the equation. And if we know something about the reaction, so if we know how much of a reactant we started with, we could figure out how much product we make. We could also figure out how much of the other reactant we would need. If we know how much product was made, we could actually calculate backwards and figure out how much of the reactants we started with. So there's a lot of different types of calculations that you could do in stoichiometry. And in terms of the units that we oftentimes come across in terms of stoichiometry, they can be moles, it can be grams, they can be liters, or they can be other units. But mainly for our class, we pretty much only see kind of the grams. And usually what you need to do is take the grams to moles. So that is usually, you know, sort of the process in terms of the conversion that you typically have to do. But they technically could be any units. They could have something like pounds, for example. You could take pounds to grams, grams to moles. You know, they could be any type of unit. And this is basically what is sometimes also referred to as the mole method. And the mole method means that we basically go to the equation and we find relationships that are there based on the coefficients. So for example, if we had this balanced equation here, let me write one here, maybe. Kind of erase that there. Okay. So let's just say we had this equation here. We had H2 plus O2 makes some water. Put a 2 there, put a 2 there, and we're all balanced. So first off, we're balanced, and we could go through this equation here and basically find 3 relationships. We could say that for every 2 moles of H2 that I put in there, and again, the 2 is the coefficient from the balanced equation, I has to put in there 1 mole of O2. And again, the 1 comes from the coefficient that would technically be here. I could also say for every 2 moles of H2 I put in there, I get out 2 moles of H2O on the product side. I could also say for every 1 mole of O2 I put in there, I get out 2 moles of H2O. These are the 3 what are sometimes referred to as stoichiometric equivalents or equivalents that you could get from this equation. They are not equal to each other in terms of numbers, right? Obviously, 2 does not equal 1, but they are equal to each other in terms of proportion. So in terms of proportion, kind of like when you make cookies or something like that, you have to throw in so many eggs, so much sugar, so much flour, I've been told, right? To mix it all up to get like a dozen donuts. I made donuts to get a dozen cookies. Same idea here. That's basically what these relate to. In order to produce those 2 waters, you have to put in there 2 moles of H2 and 1 mole of O2 to get that. So it's sort of like a proportion. So again, even though we say they're equal to each other, we're not really talking about equal to each other in terms of numbers, but we're talking about equal to each other in terms of proportion needed for this reaction to take place. And because they're technically equalities, from any of these equalities, we could write 2 conversion factors. So for example, for the first one there, we could write a conversion factor where we say for every 2 moles of H2, I get 1 mole of O2 on the bottom. Or you could write the opposite. For 1 mole of O2, I get 2 moles of H2. And that would be the 2 conversion factors you could get from that relationship. For the second relationship, you could also get 2 conversion factors. You could say 2 moles of H2 gives me 2 moles of H2O, or 2 moles of H2O gives me 2 moles of H2. And lastly, for our third sort of relationship, you could write 1 mole of O2 gives me 2 moles of H2O, or 2 moles of H2O gives me 1 mole of O2. So from this one balanced equation, we essentially can come up with 6 different conversion factors. Now, you may not need to use all of them, and you shouldn't use them all. You most likely will only need to use probably one of those in a problem. And the big thing about sort of stoichiometry is this, is instead of going to a table and finding a conversion factor, we find our conversion factor for these things from the actual balanced equation. And that is because in a problem, they will give you perhaps information about this guy, but you really want to know something about the guy over here at the end. And you need a way to go from the H2 in this example to the H2O. And the stoichiometry is the way it allows you to do that. Again, really just a conversion factor to do that. So in a sort of simple example here, let's say I started with 6 moles of H2, and I wanted to know how many moles of H2O would I actually make. So what you would do is you would take the 6 moles of H2, and what we want to eventually find out is how many moles of H2O. So what you want to do is go to the equation, and you have your H2 and you have your H2O. And from that relationship, we get this equality, that for every 2 moles of H2, I get 2 moles of H2O. And from that equality, we were able to write 2 conversion factors, which are these 2 right here. And only one of these conversion factors is going to work right for us. So just like a normal conversion, the 6 moles of H2 are on top. So to get rid of them, I need those 6 moles of H2 on the bottom, which means I should use this conversion factor here to do that. And if I do that little calculation where I get the conversion factor from the equation, I have just did stoichiometry. That was really difficult, but I just did it. And that's going to cancel out the moles of the H2. That's going to leave me moles of the water, which is what I'm interested in. And I think I picked right because I think I could do that. That is 2 divided by 2, which is 1. So I should end up with still 6 moles of water. And this is a simple stoichiometry problem, but that really is sort of what we're going to be talking about here. You're basically going to go to the equation and you're going to use that equation really to find a conversion factor to go from one substance in the equation to something else in the equation. And again, it's just because we can't go to a table and go, what is the relationship between these two things? So we sort of use the equation as a conversion factor. What this really means in sort of this actual equation is if I throw in there 6 moles of H2, and if everything went perfect in this reaction, I should absolutely produce 6 moles of H2O if everything went good. This is what is sometimes referred to as the theoretical yield, which is the maximum amount that you should produce in this equation. Sort of questions on that so far? Okay. So these are the steps that you could sort of follow when you're doing a stoichiometry problem. And, you know, sometimes it's helpful to follow these steps kind of step by step. Sometimes, you know, you may not have to do every step that's there. So for example, we want to write the correct formulas for the reactants and products. This would be a case where you're not given the equation, but you're given everything in words. So as we talked about when we're talking about balancing equations, you always want to make sure you start with the correct formulas and not worry about the balancing part. Then the most important thing in terms of an equation and stoichiometry is this step right here. Nothing will work out right if your equation is not balanced. So if you're doing some type of stoichiometry problem, you always got to make sure that this thing is balanced. Otherwise, nothing's going to be right. Yeah, so pretty much if it's a stoichiometry problem, to answer your question, you will use the equation to make a conversion factor. And that's because in these type of problems, what essentially happens, like I said, is they'll give you information about something in the equation, but that's really not what you're interested. You're interested in something else in the equation. So you will always kind of turn to the equation, the balanced equation, to get that conversion factor. And it simply is doing nothing more than taking you from one sort of substance in that equation to something else in that equation. And that's really what stoichiometry is. It's nothing more than really a conversion factor. And you just get that conversion factor from the actual equation rather than like a table or something like that. So definitely always important that the equation is balanced. If let me think here. If the equation is not balanced, you want to make sure that you do balance it. So what I was going to say is you probably see some numbers in there. You know, it's probably going to be balanced. If you see an equation and there's no coefficients in front of things, you probably should take a moment to actually put the numbers in, yeah, and make sure that it is balanced. Could be balanced if you don't see numbers, but if you don't, probably should check it. In this class, if you do see numbers, it's probably balanced, but you know, it's always good to take a second and basically just to make sure. Then once you do that, the next thing you want to do is convert grams into moles. So whatever they give you, you want it to get it into moles. And like I said, usually that's taking grams to moles to do that. And the way that we do that is what we were just talking about, using the molar mass from the periodic table, which is grams per mole. So it doesn't always have to be in grams. Like I said, you could have some other unit, but whatever you want to do is usually at some point, whatever unit is in, you want to get it to grams and then get it from grams to moles is sort of the pathway that you want to go. Now, if it already is in moles, just skip that step. So sometimes people do weird things like they take it from moles, take it out of moles, and then re-input them back into moles and stuff like that. So if something is done for you, just move on to the next step. Don't undo it. The next thing you want to do is actually the stoichiometry part. So the next thing you want to do is go to the equation and find the two things you're interested in and find the mole to mole relationship. Again, that is no calculation involved. It is just simply the balance equation, the coefficients. So in this one I just put up here, I could say that there are 2 moles of A gives you 3 moles of C. And from that, I could write my 2 conversion factors. And I want to use whichever one I need to cancel out the units correctly. And when you do that, the last thing is you may have to convert those units. You will always be in moles at this step. So you'll always be in moles at this step. So you may have to convert it to some other unit like grams. It's a very common conversion. So a lot of times at the end, you'll sometimes have to use the molar mass as well at the end to actually do the opposite, go from moles to grams. So those are some very common sort of conversions and stuff to use. Any questions on those steps? And we'll do some here together to see how we go through all those steps. Really, there's basically 4 steps when you do a stoichiometry problem. And if you just follow the steps sort of step by step, you should really get to sort of the right answer every time. So here's another sort of equation. And again, from this equation, we can come up with several different relationships. One being 2 moles of CO gives us 1 mole of O2. We could also, as we'll see on future slides here, 2 moles of CO will give us 2 moles of CO2. We'll also get 1 mole of O2 gives us 2 moles of CO2. So again, in this case, they're what I refer to as being stoichiometrically equivalent to each other, which basically means they're qualities. So for each of these, again, you can write 2 conversion factors. So for example, for the first one, I could write this are the opposite. And for this guy and this guy, you could write 2 more conversion factors. Again, you won't use them all, obviously, in a problem. You typically will only use 1, but you just want to think about it like a regular conversion. Which way is going to get my units to cancel out correctly and leave me with the right units that I need? So here are some of those conversions. And like I said, we have our other ones in there, which we can write our other sort of conversion factors for. Any questions on that there? Okay, so let's take a look at an actual problem and kind of put all the steps together. Are really, there was more than 4 steps on that little chart that I showed you, but in most sort of stoichiometry problems probably that you'll come across, there really is sort of 4 steps to follow. So let's take a look at one here together to kind of see what is going on. So in this one here, we have lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water? So really the 4 steps here. The first step that you want to do is you want to make sure you have a balanced equation. So in this case, we're not given an actual equation, but we're given things in words. So when we're given things in words, we want to just write the right formulas. So lithium metal is just lithium by itself, no charge. Reacts with water, which is H2O, which would be this guy. To form, that means that's going to be on the product side. Hydrogen gas, so hydrogen by itself in its gas form is a diatomic molecule, H2. And lithium hydroxide, lithium is +1, and hydroxide is a polyatomic ion, which is -1. That gives us LiOH. So you can see here that I just wrote an equation. What I did there was I wanted to make sure that everything was correct in terms of the formulas. I did not worry about balancing. Now that I have this equation is no good to me if it is not balanced, especially if we're doing this type of problem. So we definitely want to go through and balance it. And if you balance it, it looks like perhaps I need a 2 here, a 2 here, and maybe a 2 here. See how I did there. Just kept putting 2s. Let's see how I did. 2 lithium on both sides. We have 4 hydrogens on the left, 2 hydrogens in the first one, and 2 in the second on the right. That's 4, and 2 oxygens and 2 oxygens. So I am good so far. So definitely that is the first thing you want to always make sure you're starting with a balanced equation, or none of this is going to work. So number two, what you really want to do is take whatever they gave you and convert to moles. So when we look in this problem, we're only given one piece of information, which is we are starting with 5.32 moles of lithium. So I got 5.32 moles of lithium. So the question is, do I need to convert that to moles? I hope the answer you're saying to yourself is no. I see shaking of head, so that's good. So no, because it's already in moles. So we don't want to like mess it up. We don't want to undo it. It's already done for you. That's actually a good thing. So that second step is already there. If it wasn't in moles, for example, if it was in grams, you would need to use something to convert it into moles. And again, that would be like the molar mass calculation we did earlier on in this chapter. So since we have already have it in moles, we want to do the third step. And the third step really is the stoichiometry part. It is the mole-to-mole relationship that you need to find. So this is really where you go to the equation. I'm going to try to write that, G. Go to the equation. And you really want to find the two things you're interested in. So the way you figure out kind of the two things you're interested in is obviously one thing that you're interested in is whatever they gave you. So in this particular case, they gave us the moles of lithium. The other thing that you're interested in is what you're trying to find. So I've now forgotten, but I think we're trying to find how many moles of H2. So that is what we're trying to find here. So right here. So if you even put two boxes around it, a box on each of those, we now want to use the equation, and this is the big stoichiometry part. This is the part where we find that conversion factor. And from the balanced equation, we could say that there is 2 moles of lithium gives us 1 mole of H2. And again, this is nothing more than the actual coefficients in the balanced equation. There was no calculation kind of done to figure that out or anything like that. Now, from that relationship, as we've been talking about, we can write 2 conversion factors. So our relationship was for every 2 moles of lithium, we get out 1 mole of H2. Which means if we wanted to, we could write 2 moles of lithium over 1 mole of H2, or 1 mole of H2 over 2 moles of lithium. So here comes the big stoichiometry calculation. We're going to take the 5.32 moles of lithium that we were given in the actual problem. And remember that what we are trying to figure out is how many moles of H2. So what we want to get rid of in this calculation is the moles of lithium, which means lithium needs to go on the bottom. So we do need to use this conversion factor to help us do that. And that's going to be 1 mole of H2 up on top and 2 moles of Li on the bottom. This again comes from the balanced chemical equation. That is the stoichiometry part. That's the part that's going to get rid of the moles of lithium. That now leaves us what we're actually looking for, which is the moles of H2 in terms of our units. And maybe my calculator will stay on for enough to divide it by 2 since it's late. 2.66 moles of H2. So that is the third step. That is the stoichiometry step. And as you could hopefully see, it really is nothing more than just a conversion. Now, there typically is a fourth step, and the fourth step is to take the moles and convert it to another unit. And in this particular case, we don't need to do that fourth step because we were asked for how many moles, which is this answer right here. So we actually can put a box over this, and that would be the answer. So we actually don't need to do the fourth step. I will say that those 4 steps, no matter how scary the equation may look, no matter how scary the numbers may look, if you start at the first step and just continue on to the 4th step, is always the same 4 steps in these stored problems. So you'll never have any weird things happening in this class. You'll never have any weird stuff happening in terms of the stoichiometry. It really is just those 4 steps. And like we did here, if some step is already done for you, like it's already in moles, you just go to the next step. Any questions on any of those steps there or any part of that calculation? Yes. Why don't we do that? We'll finish this up here for just a second, and I used the formula H2 as a question because that's what it asked us to find. It asked us to find H2 in the actual problem, so we weren't looking for H2O. If we were looking for H2O, we would have had a different mole-to-mole relationship. So in this particular problem, we were interested in the H2. So that's actually a good idea. Let's finish this out like they did ask us. So that's a good question. So let's do it that way. Let's finish it out like they did ask us to actually figure out the grams. So they didn't ask us, but we'll just say late addition here. How many grams of H2 would that be? So in that case, if they did want you to figure out grams, we would have to go to this 4th step. And because in the 3rd step, you will always be in moles, we need to convert the moles now into grams. So that's going to require the molar mass. But we got to remember that we have now converted to H2, not lithium. So what we need to find is the molar mass here of H2, which again we would get from the periodic table, 2 times 1.008 grams per mole would give us our molar mass for H2. So that's like 2016, I believe. 2.016 grams per mole. And if we were asked for grams in this case, what we would do is continue on with our calculation. So 2.66 moles of H2 that we got from step 3. We would do a conversion using the molar mass. In this case, moles are on top, which means moles should be on the bottom, and it should be 2.016 grams of H2 on top. The moles would cancel. And in this, we would end up with 5.36 grams of H2. So if they did ask for grams in this particular case, you basically would go to step number 4 and continue on with the molar mass here and convert those moles to grams like we did at the beginning of this chapter. And basically what both of these numbers represent in this particular example is if we threw in there the 5.32 moles of lithium, everything went perfect in this reaction. We weren't klutzes or spilled anything on the floor. We should get out 2.66 moles of H2, and 2.66 moles of H2 represents 5.36 grams of H2. Any questions on that there? So I will say this, sometimes what people do with molar mass is not correct, and it really does happen in stoichiometry sort of calculations. And so, for example, sometimes what people will do is they'll go, oh, I need the molar mass, say, of water. We didn't need it in this example, but just say, for example, you needed the molar mass of water. And what people will do when they go to calculate the molar mass is go, oh, there's a 2 in front of it, so I should definitely multiply my molar mass by 2. So if you wanted the molar mass of water, you should only use the formula, which should give you 18.02 grams per mole, not 2 times that because of the coefficient. So it's a very common mistake people make because they will use the 2 in the molar mass, and then they'll use the 2 like in the stoichiometry part, and then they'll be off in terms of the numbers. So if you ever are looking to get the molar mass of something, regardless of what the number is in the equation, you should only use the formula to figure out the molar mass. One of those formulas to get the molar mass. And that's a very common mistake that sometimes people will make. Questions on that? Okay. So why don't you try this one? Same equation. Here we are starting with 81.75 grams of lithium. And we want to know how many grams of H2 should be produced. So let me give you some numbers in case you don't have a periodic table. Lithium is 6.941 grams per mole. And hydrogen is 1.008 grams per mole. So why don't you take a couple minutes here, follow the same 4 steps, and get yourself to how many grams of H2 would we produce here. See what you come up with. Okay, so let's take a look and just see how we're progressing. So again, I highly recommend 4 steps. Just follow those steps. So the first step is to make sure we have a balanced equation, and we already have that. So step number 1, we're good to go since we did it last time. Step number 2 is to take whatever they gave us and convert it into moles. So in this case, they gave us 81.75 grams of lithium, and we want to convert it into moles. So we definitely need to do that in this case. So we would go, obviously, if it wasn't given to you, you would find this on the periodic table underneath lithium symbol. So that's our first sort of step here. We're going to go 81.75 grams. Again, we're going to use the molar mass as a conversion factor. In this case, we got grams on top, so we do need to put the grams on the bottom here. Moles on top. Grams will cancel, and we will get 11.78, we'll call it. Moles of lithium in this particular case. I'll be honest with you, probably for our class, not so much you need to worry about the phases or anything like that. If you know them, you could put them there. But you don't really need to know the phases to kind of do a stoichiometry problem. Really, the important thing is to know the actual correct formulas for everything and then balance the equation correctly. That's sort of the most important thing. The phases is good to know, for other reasons, but truthfully, in terms of the math part of it or the calculation part of it, if you don't know the phases, you're okay as long as you really sort of know the correct formula. So that's kind of the most important thing. Other questions on that there? Okay, so we did our second step, which is convert it to moles. Third step is to actually go to the equation and actually do the stoichiometry part. We want to find the 2 things we're interested in. And we want to find the mole to mole relationship. And that's the really reason why we are converting these to moles to begin with, because we're using that mole to mole relationship as a conversion factor. So we do need to convert those things to moles to make sure everything cancels out. So just like before, one thing we're interested in is what they gave us, which is obviously the 2 lithium. And the other thing in this case is actually we're still looking at H2. So we're still interested in the same relationship as we had in the first problem. So we will have the same relationship that 2 moles of lithium, which is just the coefficient, gives us 1 mole of H2. And since we're using the same relationship, that will give us the same 2 possible conversion factors to use. And in this case, we wanted to see which one would work best. So we're going to start with our 11.78 moles of lithium. So we want to get rid of the moles of lithium. And they're on top, which means, again, we need them on the bottom. So we will use the conversion factor on the right here. And that would put 1 mole of H2 up on top and 2 moles of Li on the bottom. This is the big stoichiometry part. We're going to get rid of the moles of the lithium. We're going to divide it by 2, and that almost takes us back to 5.89, I think. Moles of H2. Last step is to convert the moles to some other unit. And the question is, do I need to do that in this case? And the answer is yes, because what I am actually looking for is grams of H2. So we do need to do that conversion. We need to take it here to grams. That again is like we kind of added onto our last problem, going to require the molar mass. Again, we have converted to H2 at this point. So we need the molar mass of H2. And that is going to be our same 2.016. And again, we calculated that in the previous example. So to finish up this calculation, 5.890 moles of H2 we're going to really multiply by the molar mass here, 2.016 grams up on top, and a mole of it on the bottom. Moles will cancel, and looks like 11.87, which I think is what I saw fly by there in the chat, which is good. 11.87 grams of H2 would be produced. So again, what this really means in this reaction is if we put in there 81.75 grams of lithium into this reaction and everything went perfect, you should expect to be able to collect out of that reaction 11.87 grams of hydrogen being produced. Again, that is sometimes what is referred to as the theoretical yield. Hopefully you can start seeing some pattern here. You can see that it is really the same 4 steps. So again, step 1, balance equation. Step 2, convert to moles. Step 3, mole to mole relation, the stoichiometry part. And step 4, the moles to grams part, or moles to some other unit. Again, doesn't always have to be grams, could be some other unit. Now you can see I did this step by step and got an answer after each step, which is perfectly fine to do. I probably went around too much at each step though. You could also do this entire calculation in one step, one sort of calculation after the other, and put them all together is perfectly fine. Any questions on any part of that, where any of the numbers came from, why we found any of those things? Okay, so now that you're professionals, let's try another one here. That's the same one, so let's try this one. All right, so you give this one a go here. Take a couple minutes to see what you come up with. We're going with 765 grams of C6H12O6 is consumed. What is the mass of CO2? So we're looking for grams in this case. So how many grams of CO2 is produced? Let me give you some numbers in case you don't have a periodic table. Carbon is 12.01. Hydrogen is 1.008. And oxygen is 16. So again, follow those same 4 steps. And again, should hopefully lead you to the right answer. So see what you come up with. Okay, so let's take a look at this one. So same idea here. We want to just follow our same 4 steps. So I see an equation, I see some coefficients, and if I quickly kind of look through it, it is balanced, so that's good to go. Second step, again, is to take whatever they gave us and convert to moles. And in this particular case, they gave us 765 grams of our C6H12O6. That does mean that we do need to convert to moles, and we are going to need the molar mass of our C6H12O6. Again, that's going to come from the periodic table. So 6 times 12.01 plus 12 times 1.008 for the hydrogen, and 6 times 16 for our oxygen. And it looks like if we do all that, maybe 180.2 grams per mole. Again, we're going to use that really as a conversion factor to take what they gave us, which is in grams, and convert it into moles. So we will just start with that part of the calculation, 765 grams of C6H12O6. Again, really using the molar mass as a conversion factor. Our gram's going to go on the bottom there, so that's 180.2 grams per mole. Grams are going to cancel, and that will get us, in terms of moles, 4.25, we'll call it. Any questions up to that point? So again, this is just like the calculations we did at the beginning of this chapter, using the periodic table to get the moles per, the grams per mole, and really using it as a conversion factor. That then brings us really to the big stoichiometry part of the event here. We're going to go and find our really mole to mole relationship, and we're going to find it between the two things we're interested in. So obviously in this case, we're interested in our C6H12O6 that was given to us. And in this particular case, we're looking to find how much CO2 we would have. So from the equation, we see that for every 1 mole of C6H12O6, that gives us 6 moles of CO2. So like we talked about before, you could get yourself 2 conversion factors from that. One that looks like this with our CO2 on the bottom, and one that has the CO2 up on top there. Again, we want to choose the one that's going to help us. So we do want to get rid of this guy. So it won't always be the guy on the right, which just happens to be under these examples here, but it will be our guy here on the right that's going to allow us to do that. So that again is sort of the third part of the calculation. That's the big stoichiometry part of the calculation. And continuing on, we had 4.25 moles of C6H12O6 using our conversion factor on the right. That's going to give us 1 mole of the C6H12O6 and the 6 moles of CO2. Again, this is coming from the balanced equation is where we're getting that relationship from. So we're essentially going to multiply this by 6, it looks like. And that'll give us something like 2547, I believe, if I'm not mistaken. And if we want, we could do a little bit of rounding, 25.5 moles of CO2 at this case. We have now just used stoichiometry to go from the C6H12O6 to our CO2. And what's left would be step number 4, which is to take what they gave us in terms of moles at this point and convert it to some other unit. And since we are looking for grams, as I mentioned earlier, we do need to do this part. So remember at this point, which is also sometimes where people mess up, we have now converted into CO2. So we do need the mass of the CO2 to do this at this point. And that means going back to the periodic table, 1201 for our one carbon that's present, and 2 times 16 for our 2 oxygens that's present. That's a 4401 grams per mole is the molar mass of CO2. So finishing up our calculation here, 25.5 grams, not grams, not yet. Let's go with moles. Almost there. All right. Moles of CO2. Using the molar mass of CO2 as a conversion factor, grams going to go on top because that's what we're looking for. Moles will go on the bottom. Moles cancel. And that would get us timesing 44.01. That will give us something like 1,121 grams of CO2. Or if you want to do some sig fig right, 1120, no decimal, grams of CO2 in that particular case. Question on any of those steps? Again, you could hopefully see exact same 4 steps. We had some bigger numbers here. We have some scarier looking formulas here as well, but it is still the same 4 steps as you go through it. And this is, again, what I was kind of pointing out earlier as well. When I went to go get my molar mass for CO2, again, even though there's a 6 in front of it here, it has no effect on the molar mass. The molar mass should always be based just solely on the formula. And that's why it's per 1 mole. The place where we take care of the 6 in these type of calculations is right here. So if you did the 6 here and then decided I want to do the 6 over here, you're going to mess up and get the wrong answer. So again, very common mistake that people make. They go to do the molar mass and they take into account the coefficient again. And you should never, ever do that. You're calculating molar mass, strictly straight formula. That's how you should do it. Any questions on any of those steps along the way there? I think you shouldn't get that if you just kind of did it all in one step. Here, let me just punch it in if my calculator survives. Let me try this here. So we started with 765, and then we had basically, if you did it all in one step, you would have been multiplying by 6 and multiplying by 4401, and then dividing by what we have, the 180.2. I still get 1121 when I punch it all in. So it really should come out the same, whether you break it up in parts or you did it all in one calculation. It should really kind of come out the same, as long as you don't really round too much in each of the steps. So my guess is if you got 1529, maybe some numbers off somewhere along the way would be my guess. Other questions on that? Okay. So why don't you try one other one here and see what you come up with. So we're looking for how many grams of cisplatin in this guy. Scary formulas. They did give you the molar mass of each of these. So these are the molar masses, like you would go to the periodic table for each of those. So you don't have to worry about it. So that's pretty good. So see what you come up with. Okay, so since we're getting towards the end here, let's take a look. So again, let us follow the same steps. So step number one, we do have the equation. It is balanced. Step number two, we take what they gave us. So again, although there's three numbers, this number here is really what was given to us. The other ones are really the numbers that you could get from the periodic table. So it saves you a lookup time. So we're going to start with that, which is 0.7752 grams of K2 PtCl4. And again, here we're going to use the molar mass, which they were kind enough to give us. If they weren't, to the periodic tables where you would have to go and add it up like we did all the rest of them. We're just going to do a conversion here, getting rid of the grams. So on the bottom should go 415.1 grams per mole of our KTPTCl4. At this point, we can go to the equation and find the two things we're interested in. So one thing is what they gave us, which is right here. And the other guy that we're interested in is this scary guy over here of all those symbols. And although they all look really scary, it is still actually a 1 mole to 1 mole relationship based on the coefficients. Let's write it this way since I'm going to run out of space of the PTNH3 to Cl2. So 1 mole of our reactant gives us 1 mole of our product. And just to show you again, you could do it all in one step. I will not get an answer at this point, and I will just kind of continue on as well. Again, the grams will cancel here. I have the moles of the KT PTCl4, so I need those on the bottom. And up on top is what I'm looking for. And that is going to cancel those two. And if I stop right here at this point, I am in moles of the product, but we don't want moles. We do want grams. So we do need to do that last step where we convert it from moles back to grams using the molar mass, which they were nice enough to give us as well, which is 300.1 grams per mole of this guy. These moles will cancel, leaves us grams. Again, if we multiply everything across the top, we're going to take 0.7752 times 300.1 and hit equals, and then divide by 415.1, hit equals, and it does look like we end up with 0.5604 units now are grams of our product. So as I think was the earlier question, you can do it all in one calculation. You could do it like we did before, where you went step by step. It's perfectly fine. Either way, again, don't round too much if you do step by step like we did before. But even in a all together move, it is still the same 4 steps. Here's step number 1. This is step number 2, convert to moles. This is step number 3, which is the stoichiometry step, mole to mole relationship. And that is step number 4, which is convert the moles back to grams. So even though this one again looked really scary perhaps with all the formulas and stuff going on, it is basically for this class always the same 4 steps. And like I said, start at the first step, continue to the next one, to the next one, to the next one. Something done for you, just move on to the next step. Question on stoichiometry or any of those sort of things we did here? Okay, we will stop there for today. A couple reminders before you guys take off if you have lab today. A reminder that 1 week from today is our first exam. It is going to cover, again, chapters 1 through 4. You will not be given any polyatomic ion names, so you do need to know those. You will not be given geometry names, so you do need to know molecular geometry names like we talked about. I also put up on Canvas a kind of separate polyatomic ion list to kind of has them all kind of together for you, which might be helpful as well. In addition, since it does cover chapter 4, a reminder that the recorded lecture for chapter 4 is like 50 some odd minutes is up there. So make sure that you do watch it. because that stuff will be part of the exam as well. We will take the exam during lecture time, so we'll start around the start of lecture, and you'll have the entire lecture period to about 7, probably, to take the exam. You need to start it, obviously, when lecture starts, and you'll take it just like you took the quiz, using proctorial and all that. The difference is there will be, again, a multiple choice part for this exam, much like the quiz, but there will also be sort of a written part where you'll need to work out some problems and show some work, and then upload that work as part of your exam. The homework, again, is due on exam day, and I had some questions about that. I don't usually post the upload until exam day. I might do it before that, but I usually just post it on exam day since everybody has it and is ready to kind of turn it in at that point. So I might put it up earlier, but that's usually when it'll be up there. So minimum, again, in terms of the homework, you do need to do every other one that's listed. So there's just a minimum for everybody that does sort of the same amount. Like I said before, truthfully, I'm not going to look that closely, as to which ones you actually did, but I would highly recommend that you definitely do every other one is listed, because what that will do is give you problems throughout the entire chapter. If you just do like the first ones, you're going to miss half the chapter and stuff like that, and you won't really have practice. So the benefit is for you to do all that. The test on the grade will be, when I grade it, hopefully within the week. I don't know, but it should be usually within a week of you taking it. You should have your score. So it's a lot of tests to go through and adjust grades and grade and stuff like that. But usually it doesn't take longer than probably a week and stuff like that. Yeah. It does start at lecture time, and since technically half of you will have lab and the other half obviously has discussion, it will be done before lab starts, like at 7-ish. Yeah. So that time around. I actually teach and stuff like that. So we have discussion today. If you have discussion today, if you have discussion on Monday, good opportunity to ask questions and stuff like that. Okay. You don't need a code for the exam if that's what you're asking. If it ever asks you for a code, it means that you don't have the proctorial and all that set up correctly. So it shouldn't really ask you for a code. Okay. Any other questions on that? Okay, so if you're off for a lab, have a good weekend and stuff. I'll see you on Monday. If you have discussion, since we're going a little bit longer, we'll start about 7:05. Give everybody a chance maybe to stand for a minute or two. And like I said, if you have questions about the upcoming exam, I'll be happy to answer those during discussion today. And then obviously, if you have discussion on Monday, you can ask those questions on Monday as well. All right, I'll see everybody in about 5 minutes if you're coming to discussion. Otherwise, have a good weekend.